Hi, my name is Stephanie, and today, along with my group members Sujith and Michaela, we will be presenting our current findings for the IC Engines lab. The basic rundown is that the company Generative Energy wants us to determine some defining parameters and controls for a four-stroke IC engine. The main theory to be used to characterize the engine is a work energy balance, which accounts for energy transfer and work done by different components in the engine. To find different parameters, a series of experiments will be performed in which changing the setup of the system will allow for the equation to be manipulated and allow for variables to be found. Presented is the experimental setup. The major components are the force transducer, moment arm, motor shaft, pistons, flywheels, and encoder sensor. These are needed to obtain different metrics such as time, encoder angle, force in volts, and many other metrics that will allow for the calculation of the different parameters in our work energy balance. The significance of each component is as follows and is presented on the screen. For the force transducer, it must be recalibrated every time to ensure transmission between voltage and torque is correct. I will present those later. The motor shaft and encoder are needed for indicating the position of the piston, which is important for defining work done by different parts of the system. The pistons is of course the main item that we are observing and is needed to characterize the behavior of the entire system. The flywheels are needed as we will calculate the moment of inertia to relate the energy transfer part, which was the left side of the work energy balance presented before. Presented is the force transducer calibration performed weekly to characterize the relationship between the torque and voltage. Data was collected by placing weights on the moment arm and then calculating a torque. The emitted voltage by the weights was recorded using LabVIEW. Using Yort's regression, the gain and offset were found. For week 1, gain was found to be 0.7053 with an offset of 0.6250. We see a change in week 2 where the gain was found to be 0.6953 with an offset of 0.7708. Something that should be noted is that there is a gap between the data points. This was due to hysteresis occurring because of the loading and unloading of the weights. From these calibration equations, the torque measured during experimentation can be transferred from voltage to Newton meters.
The main equation when trying to characterize the engine is shown at the top of the slide. This includes variables for the moment inertia of the flywheels, the angular velocity of the crankshaft, work done by the air, work done by the motor, work done by friction, as well as work done by the piston. We're assuming that the work done by the piston is 0. However, even with this assumption, we have too many unknown variables. The only variables that we do know are the work done by motor, which can be calculated using data from the force transducer, as well as the angular velocity of the flywheel. The first step that we could do to eliminate variables is the characterization of the engine with the head removed. So this eliminates the work done by air variable, but still leaves us with the moment of inertia of the flywheels as well as the work done by friction. A further simplification is looking at the engine with the head removed, but also during steady state. This eliminates the change in angular velocity on the left side of the equation and cancels out the I-fly unknown term, which leaves us with the work done by the motor and the work done by the friction, which we can calculate. So after we calculate the work done by the friction, we can find T friction. And T friction can be used to find I fly as we go back up to the characterization of the engine with the head removed, but not during steady state. So the moment of inertia of the flywheels is equal to 2 times negative work done by the motor plus T friction times the change in angle divided by the angular velocity squared. Here we have the torque versus angular position graphs of the different experimental setups with the head removed from the engine. We tried 3 different applied voltages as well as 2 different moment of inertia settings, one with 4 flywheels and one with 1 flywheel. So here are the graphs for the 4 flywheels, and similar analysis was done for 1 flywheel. As shown in the previous slide, we were able to use the steady state portion of the graphs to find work friction as well as T friction. However, one of the main assumptions that we had to make in order to use T friction to find I fly in the next part of the experiment was that Angular velocity and T friction were independent of each other, so T friction was constant regardless of angular velocity. However, as shown on the graph on the bottom right, there seems to be a positive correlation between angular velocity and T friction. As angular velocity increases, T friction also becomes larger. So this may be a weak assumption that we may need to change in the future.
Now that the work due to the motor and T friction have been found, they can be used to find flywheel moments of inertia. A theoretical value was calculated using a disk moments of inertia formula, which is in equation 1. The experimental I-flat was found using equation 2, where we used the found values of T friction and angular velocity. I-flat was determined experimentally for 4 and 1 flywheels. From this data, we can see that there is some difference between the theoretical and experimental values, where the experimental is higher than the theoretical. This can be due to many reasons, but one is that the theoretical flywheel equation assumes that the flywheel is a perfect disk without any additions such as screws or rods, as seen as those that are present in our experiment. Additionally, the experimental values used have some calculations with simplifying assumptions, which may contribute to the different discrepancies we see between the two values.
To characterize the four-stroke cycle of the engine head was reattached so that air pressure was reintroduced into the system. The experimental inertia of the flywheel and the work due to friction were found during the previous experiments discussed and inserted into the work energy model. With these terms known, we can now update our work energy model to look for the work due to air pressure. In this portion of the experiment, 3 different velocities were tested for 2 inertias each. 3 seconds of steady-state data were recorded for each test. For each of the velocities tested, the cycles recorded were identified and averaged together to yield representative cycles with lower uncertainties than the raw data. The 4 strokes of the engine are intake, compression, power, and exhaust. During the intake stroke, the piston moves down and draws air into the cylinder. This air is then compressed during the compression stroke, when the piston moves back up. The pressurized air then drives the piston back down during the power stroke. During the exhaust stroke, the spent air is expelled from the system as the piston moves back up to the top. Because our data was recorded in steady state, the starting angular position of the flywheels was variable, so we needed to identify each of the strokes of the 4-stroke cycle. The power stroke could easily be identified by locating the stroke which correlated with the highest torque in the system. Once this stroke was identified, the other strokes could be found by iteratively adding 180 degrees to the immediate previous angular position. The work terms that are the highest in magnitude are found in the test with the highest velocity at 0.9 volts, and the lowest terms are found with the lowest velocity at 0.3 volts. Notice how for the cycle driven by 0.3 volts, the work during the power cycle is negative. This tells us that the motor is driving the engine rather than the engine driving the motor. The same process as discussed for the 4 flywheels was followed for the single flywheel. The work terms due to the air for each of these velocities are noticeably lower than the previous values found with the higher inertia. The upcoming experiments will focus on modeling the engine with simulated combustion. Pneumatics will be used so that the engine will drive the motor. During this experiment, we will test different ranges for the pneumatic valve to be open for varying angular positions of the flywheel, with the goal of maximizing the power output. We will complete our work energy model as well as calculate uncertainties, and we will analyze the work due to air over the course of the whole cycle as well as only during the power cycle to determine limitations in the system such as leaks.